In this video, we are going to see how we can read and write through the GPIO pins of the RA6M4. In a 144-pin package of the RA6M4, there are 109 pins that can be used as general-purpose input and output. They also come with internal pull-up resistors. 21 of these pins are also 5-volt tolerant against the usual 3.3-volt operating voltage of the RA6M4. The EK board comes with user configurable LEDs and 2 user buttons. To access these peripherals, the corresponding pins need to be configured as input for the switches and output for the LEDs. We are going to write a program that will configure the LED pins as output on the press of a button and then toggle a blink sequence on the press of another button. The LEDs will not light up unless their pins have been configured as output, regardless of the status of the blink sequence. This will show an effective use of the pin read, pin write, and pins configure APIs. As usual, we will start with a new workspace. We will create a new project and name it My GPIO. We will select the EK RA6M4 board and click Next. We will keep the settings to default and select the minimal project template. Once the project has been created, we will configure the pins. From the Pins tab, we can see that some pins have already been configured for the EK RA6M4 board. We will make a duplicate of this configuration to customize some of the pins, specifically the pins attached to the buttons and LEDs. We will amend the name of this configuration with an added underscore GPIO. Every time we generate the project contents, we shall now have 2 configurations. We will first make changes to the default EK configuration. The pin 415 is connected to the LED 1. We will disable it. In the same way, we will disable the pin 404, which is connected to the LED 2. This means that when the default pin configuration is loaded, these pins will be inaccessible by the program. Then, we check that the new configuration we made still has the LED 1 pins set as output. Next, we will check the pins 005 and 006, which is connected to the user buttons. By default, these are set as interrupt pins. So, we will first detach them from the interrupts, and then we will set them in input mode with pull-up enabled. We will do this for both the configurations. In the RAGen folder, we will find the pindata.c file. This file contains all the configuration for the pins. We can see that there is only one configuration. Once we have generated the project contents, we will see that a second configuration has been created and added to this file. We then move on to writing our code. In the hullentry.c file, we will first initialize the variable to hold the status of the blink sequence. Then, we will initialize the variables for the error status and the variables to hold the input states. For the input states, we will use a custom data type that holds the value for high and low input. Then, we will make the while loop. We will not need to call the Open IO port API separately since it is already part of the code template in hullentry.c file. The next step is to populate the while loop. Our first two API calls will be the pin read API, which can be found in the Developer's Assistance menu. We will add two instances of this API for reading the levels of the two user buttons. We will also add the assert macro that assures that the API call has been executed successfully. In the pin read API, we will need to insert the name of the user button or the pin to be read, and we will need to add the pointer to the variable that stores the state of the pin. Once we have captured the state of the pin or the button attached to it, we will write the action items for a valid press. In the array board, pins are configured from pin function select PFS registers, which is accessed by the RIO port pins config API. On the press of S1 button, we will load the new pin configuration that we have created through the pins config API. From the pins tab in the configuration view, we can get the name of this configuration. We will insert this in the API. Once the API has been executed successfully, we will make use of the pin write API to power on the LED2. This API takes the name of the pin and the I/O level we would like to set. Next, we will see if the S2 button is pressed. If it is, we will decide whether the program should run the blinking sequence or not. We will first add a small delay, and then we will toggle the status of the blinking routine. Following that, we will set up a basic blinking pattern for LED1. If no buttons are pressed and the blink sequence is enabled, the board will continue to blink the LED. However, if the pin configuration isn't loaded, the program will execute the blink routine, but the LED won't illuminate. To activate the LED1 pin as an output, we need to press S1 first, which loads the pin configuration that has the LED1 pin enabled. Then, depending on the input from S2, the blink sequence can be turned on or off. Now, we can build our program and upload to our board. Let's check the code in action. If we press the S2 button, there is no blink pattern on the LEDs. That's because we have not yet configured the LED pins. So, we need to press S1 button first. Pressing S1 lights up LED2 that acknowledges that the pin config has been changed. And we can also see that the LED1 has started blinking. We can now turn the blink pattern on and off by pressing S2. So that's a short demo on how we can work with GPIO pins on an array MCU.